I shared a bit of the hypothesis, I think, of the talk yesterday. And essentially, the argument I think I'm going to try to convince you of is that, yes, we've been focused on improving models and processes within them, and lots of great discussion there, certainly very much needed, but there's a revolution going on around us. What's that revolution? It's all things data science and sensors and computational capabilities. And I think that's really striking me in the role I currently serve in as we look at all that's going with the ag tech startups and just the entire set of research that many people are pursuing as we certainly get into some of these interdisciplinary spaces. So let me briefly touch on model improvement, then we can zip through that because we've been talking about that. Talk briefly about some of the computational things going on, sensors and data that have been revolutionized and are continuing to grow greatly in coming years, and some of the things going in data science, and see if we can sort of stretch your imagination. So again, we've been talking about these modeling kinds of opportunities, very much needed, but I think we need to make sure we continue to think about these in light of the other advances we see in all things data science and related. Computational capabilities, people didn't talk so much about those, but we saw a number of examples in some of the modeling where people are leveraging parallel computing, supercomputing, cloud-based computing and storage. One that we did not talk as much about, but it's striking me more and more, is edge computing, where we put computing near where we have huge amounts of data being collected so that we don't flow the huge amounts of data. We flow only the necessary reduced sets of data. So we see this going on around places that sensors are generating large amounts of data. We see this around remote sensing, UAV-based remote sensing, ground-based unmanned sensing with vehicles and things. So there's a huge revolution in this edge computing concept that I think, again, we need to keep in mind as we're thinking about models and where the future might take us. Again, a quick example, and Jeff earlier in the week had examples nationally of where they're doing with SWOT huge amounts of modeling continent-wide almost. This is just a very simple example from some prior work of students where they were looking at runoff from urban areas, and so taking national data sets, pushing those through models, doing a lot of that in parallel to then get information that can help us make decisions, in this particular case related to urban runoff. So many examples of that today, and many in some of the pesticide related work, and EPA is doing some of these regionally, if not nationally, as well. So that's been a huge change in the past decade or so, and we can just imagine where that's likely headed. Sensing and data, huge revolution here with IoT, Internet of Things, with sensors and all things sort of connected. Unbelievable the change in spatial and temporal data resolution, the flows of data from federal and state and other sources. One example I thought was probably useful to point out. I'm sitting about a block from a building where some of the early distributed parameter hydrologic water quality modeling was done. And less than 50 years ago, in that space, they were sitting there with paper maps. They were overlaying acetate with squares on it and coding values into those squares that they would then lift and code into input files for computers. Just think of the advances we've made in less than 50 years with the flows of some of these data sets. Many of us also can remember the early days of some of the modeling we did where we were generating digitized data for some of these inputs as well. So we were digitizing paper-based data. So the data flows from definitive sources have been greatly changed in recent years. And again, we can think about what the future might hold. The other piece I think that we need to stretch our imagination with is the data that we've wished we had, in many cases is on the horizon as well, or the volume of data we wished we had in some cases. So again, with the sensing and flows of data greatly altering the prospects for the future. Just a recent project that from some of the group here on campus, looking at IoT and ag and use of AI and data flows, and you see remotely sensed data sets flowing and being collected as well. So again, just a revolution in some of this that's now underway. If you think this is not coming to a place near you, we have a 10 county study region in this area, much of it very remote. The group trying to promote some of this, they're buying aerostats. So blimps, small blimps that they're going to tether, and they're going to use those for IoT and high-speed transmissions of all kinds of things. So, the world is changing in some of these areas and probably changing faster in ways that we don't fully appreciate at this point. Data science, some of you have touched on parts of this with the data flows and data pipelines. I know we're seeing huge revolutions in some of the data pipelines from big data sets now flowing into processing and databases and back out and elsewhere. So lots of infrastructure being built in some of those areas. Some people had touched on machine learning yesterday and some of the AI maybe behind the scenes in some of these opportunities. We've seen parts of this before, but I think what's changed this time is there's a much bigger broad-based community. It's happening widely within industry and beyond that is now truly driving much of this. And I know there was some mention of machine learning. It requires lots of data, huge amounts of works that have really reduced the data needed in machine learning applications. So to me, that's been a very surprising difference between now and 30 years ago when we needed massive data sets for machine learning. So again, changing very rapidly, and I don't think we fully embrace and understand, nor maybe is it possible, the implications of this and some of the modeling that we're doing. I'm going to step through just a couple of quick, simple examples to sort of share, things that we have been working on for many years. This is just an example of a small watershed. If you place some practices with the conventional technique, you maybe get some improvement in phosphorus load. But if we can use AI and optimize, because we probably can't truly spatially optimize these with conventional optimization, we can spend the same money and get huge additional benefits by properly selecting and placing practices. Again, I think interesting implications as we think about pesticide kinds of issues. Following from that, we can begin to generate Pareto optimal fronts of where the potential reductions, and this just represents dissolved reactive phosphorus and total phosphorus, but where on this curve you want to operate so that you can make a trade-off between reductions, in this case in phosphorus, and what it's going to cost to reach those. Again, very interesting policy and other kinds of applications. And again, we can see how that crosses over into some of the pesticide area as well. Pulling one example off that graph. So in the St. Joseph watershed, and I think Rocky presented St. Joseph watershed results yesterday. If we pick a goal of reducing dissolved reactive phosphorus by 40%, based on a huge amount of modeling with parallel AI kinds of techniques, this is what it says the solution would be. So exactly one solution out of many, many millions of solutions that might be possible. But this one, using these techniques, says this is the one that will get us there at least cost. So again, we can think of all kinds of interesting implications and things we've been talking about. I'm going to just go ahead and move through some of these more quickly. This one's kind of interesting. So for more than 20 years, we have been running an application for Indiana and I think the neighboring states where you could go any place, pick a point, it would delineate a watershed, We see the watershed here in green. It would flow those data into a model doing some GIS behind the scenes. The key here, though, is this is a 20-year-old application at this point. We saw things earlier in the week from several presenters that have revolutionized this because of data flows. What's the big difference between today and my 20-year-old application? Well, in my 20-year-old application, there were a whole lot of people who spent months and months downloading data, processing data, adding value to the data, and then us storing that to build the application around. Today, those data flow from the definitive sources so that as they're updated, the applications see that data real time as it's updated, and it's the definitive set of data. Other applications where, again, we're going to flow data from multiple sources here, push it into an optimization AI-based tool to pick management practices. Again, it's more than 10 years old at this point, but again, I think points to the opportunities as the data are now flowing better than ever before. So this is getting flow data from USGS, it's getting pesticide data from EPA and other data from EPA, generating flow and load duration curves. It lets one then, with some AI kinds of techniques, identify practices that target where the problems likely are. That flows into a simple model in a spreadsheet here. It knows how much reduction's needed. It knows something about costs of practices, and it can develop an optimal plan and how you get there, and can do that in minutes. Just one final example here. We heard, I think Apex was mentioned a time or two, or Epic and Apex were mentioned a time or two. So just again, a simple example where this is running in the continental US. This is also running in China at this point. Former students that work with Dennis and I have this running in China. There's nothing that would prevent this from running most of the globe with not quite as good a data as we have here, but GIS mapping, zoom to a location of interest, interact, identify a field or region of interest. The model is parameterized by data flowing from national databases. Model runs in a minute or so. We get results back. We saw that with some things with WEP earlier in the week. Things that Jeff was talking about with SWAT are largely doing some of the same things. So my last slide, and I'd be happy for a question or two, and then we can probably do a break. So what might the future hold? So, and you can probably add to my list here. So we could imagine models that learn and adapt to their application area to improve estimates. You can imagine data flowing in from all kinds of places, from sensors. So we have models that are smart and learn and get better over time. That's not very far-fetched. In fact, we've got people doing some of those kinds of things now. You could imagine intelligent modeling systems that sort of build on that concept, that really help drive local decisions and make these decisions very location specific. We looked at some things that have those elements in it in my examples. We can think about potentially location specific regulatory approaches. Maybe far-fetched now, but project to the future and think about my example where less than 50 years ago, we were doing distributed parameter models by overlaying plastic on top of a paper map. Only less than 50 years ago. So what will the next 50 years hold? So that's certainly a possibility. We might even have models that are running and helping shape regulatory kinds of approaches that are location and time specific. They could evolve over time, again, based on data, based on things we see. So, what do my questions here all have in common? There's not a lot in those questions about improvement of processes and models. Doesn't mean we don't need it. It's really a lot about data science, IoT, computational advances. So I just wanted to stretch your thinking today with a little bit different view of maybe some next opportunities. We've heard, I think, much of this sprinkled within many of the talks that have been provided, but just wanted to lift this out and get you to think. Let me stop there, be happy for a question or two, and then want to give you a bit of a break. So. And you can tell me I'm all wrong too.
Hi, Bernie, this is Sarah. I think that was really great way to wrap up the week, or at least this modeling section. As a person who doesn't develop models, but sometimes uses them to answer specific questions, what are your thoughts about kind of making modeling more accessible? I think one of the biggest challenges I've seen is that there's this modeling community, and then there's the experimental community and the data people, and policymakers are kind of sometimes in both camps. I'm curious how we don't want to get to the place where, people who aren't understanding the processes and that kind of stuff are just pushing buttons and creating kind of nonsense, but not having that deep expertise in the coding components or some of the modeling tool sets, I think is really an awesome advent of some of the things you're talking about, web enabled inputs, things like that. So I'm curious your thoughts on where that is now and where that might head in the future.
No, that's a great point. So, I think, what we see is models beginning to have more intelligence built in so that they know when they're maybe being used or misused. So I think, again, opportunities like this workshop or maybe subsequent workshops, to begin to make sure the communities are talking across, some of these delineations that you sort of identified. But I think, we're seeing more intelligence, we're seeing more automated flows of data. And I think, again, and I think we heard earlier in the week that people are auto-calibrating some of these things with data flowing in. And as long as, there's some intelligence built into those, it's very difficult for application users to get too far out of bounds in some of those. But I think, you raise some interesting questions, but they're, communication across these groups going to be important.
Bernie, this is Srini. If I can add on to that, to add a few more details on that. Some of the work, what we are doing is twofold. One is, yes, data flow and model for anywhere, any part of the world. But more importantly, network of scientists working together and publishing their models, not just keeping the models to themselves to do the work that they've been doing for the last 50 years, but rather publish that model, share that model with anyone and everyone. Once it's published and if it's peer reviewed, why not that model be put to use for other applications that's not being, you don't have to reinvent the wheel or re-spend all the resources, energy on calibration validation. Why not we put that model directly to an application? So the graduate students, so that's exactly the Hawks framework that we developed with the US EPA is exactly doing that. Right now we have more than about 20 universities using it as a graduate school research tool for them to use it to basically develop models without spending hours and months and years of collecting data. They could put together a model under 5 minutes and then start using that model for a specific application. So that may be an area that we need to be thinking about down the road.
Srini, thanks. Yeah, Srini swapped in for Jeff today. Jeff's on the road, so Srini's the backup. So one more question, then we probably should do a break.
So I have a comment. Oh, sorry. No, please go ahead. Yeah.
It was more a comment maybe on your list, on your laundry list, and is so what we have been looking at mostly is mechanistic approaches to describing the world with better or less success. Now we move into the wild west of black boxes, which is essentially machine learning and so on. So the issue, I would add to your list the issue of cyber trust. It has to do with transparency. Okay, and remember, I did that trade-off between transparency and so on, and I think it's a very important question that we need to keep up front as we start incorporating some of these practices. So maybe
great point. You could imagine that somebody could develop these with sort of their finger on the calibration or other things that would tilt results. So great point. Great point. Well, I'm always happy to brainstorm about some of these things, but I think in the sake of trying to keep us somewhat on time, let's resume in about 10 minutes. So